All right, so this video is going to talk about nomenclature. We're going to focus specifically on ionic and molecular compounds. Ionic compounds are formed between metals and nonmetals, or possibly a metalloid. They result from a transfer of electrons between the cation and the anion, and that forms an ionic bond. They conduct electricity extremely well when they are in solution or when they are melted. They would not conduct electricity well if they are just in their solid state. They have extremely high melting points and boiling points. They're very hard, they're very rigid, they're very brittle. Sometimes polyatomic ions will replace metals or nonmetals in ionic compounds. These are atoms that are covalently bonded to one another that have a net charge. There's a list in your packet. There are two polyatomic cations, ammonium and mercury 1, and there are lots of polyatomic anions. The names and the formulas of those ions don't ever change. The ones I have provided for you, I do encourage you to make flashcards of. I also have a Quizlet that I will share with you to make sure that you're aware of which ones you need to know. But I do encourage you to commit those to memory. You're going to be using them an awful lot. My hope is with practice, they're going to start to stick. However it best works for you. I also encourage, if you do not recall the charges of your main group elements, that you work on getting those down. The transition metals aren't as big of an issue because you should be able to determine the Roman numerals of transition metals, the ones that form multiple cations, based on the compounds, the formulas that are present. However, you do need to know which transition metals do not form multiple ions, like zinc and silver. Those should never get Roman numerals. You also need to know that lead and tin, which are not in the transition metal section, but do and show up further on the periodic table, are able to form multiple cations, so they would need to have Roman numerals whenever they're a part of an ionic compound. Okay, so when we are writing formulas from names, we need to make sure we know what ions are present, what their charges are. That's just reviewing what the charges are of the different groups. You want to combine those ions together to make the simplest ratio that will allow the ion pairing to have an overall charge of 0. We never show charges in our final formula. And if we have a polyatomic that we need more than one ion of to make that neutral formula, we use parentheses to show how many of that polyatomic ion we need. You will never have to show me the first two columns on any assignments that I give you. This is just to kind of help you break it down. So please know that if you can go straight from name to formula, you do not have to do the middle two. So barium is in group 2, so it has a +2 charge. Chloride comes from chlorine, halogen, which is -1. So to make a neutral formula, I'm going to need more chlorines to balance out the +2 of barium. I would need 2 of them, BaCl2. With copper 1 oxide, copper is a transition metal. It is not one of the exceptions, so it does need Roman numerals. The I is telling me that this copper has a charge of +1. Oxide's coming from oxygen, which is going to be in group 16. It has a charge of -2. So to balance this formula out, I would actually need 2 of the coppers as opposed to 2 of the oxygens to balance out the -2 of O. In our next example, my hope is you can see why Roman numerals are going to be important with those transition metals or any metals that have multiple oxidation states. This time we have copper with a 2, Roman numeral II. So when we have a copper 2 with oxygen again, we see this time that they are neutral when they're added together. So we truly only need one of each of those ions present. But if we didn't have the Roman numeral, it would be hard to distinguish between copper 1 oxide and copper 2 oxide just off of their name. We need to have that Roman numeral to tell which one we're working with. Finally, with calcium phosphate, calcium is in group 2. It's an alkaline earth metal, so it has a +2 charge. We've been dealing with anions that come from the periodic table, but phosphate is one of your polyatomics, PO4 -3. Neither of these ions are able to balance out the other one's charge just by increasing them. But if we take a look, we see that 2 and 3 both have a common factor of 6. So if we bump calcium up to 6 by having 3 of them present, and if we bump phosphate up to 6 by having 2 of them present, we will end up with a neutral formula. Notice with phosphate, you needed to put parentheses around it so it doesn't look like 42 O's, but that there are 2 PO4 units present in that formula. When we're naming our ionic compounds, we find the 2 ions and we're just going to name them based on the rules that we've talked about before. Cations always get named before anions, just like cations always get written before anions in chemical formulas. The names for the metals will just be their full name unless it's one of the metals that has multiple oxidation states, and then it would get a Roman numeral. You've got some examples there to look at if you need a review. If it's a polyatomic, you just write its name down. If it is an anion, we're dealing with the second half of the compound and it's from the periodic table, we take the root of that name and add on "-ide", or we just name the polyatomic. So with these 4 examples, we're going to split the formulas in half and name the 2 ions, or identify the 2 ions and then name them. Again, you are welcome to go straight from formula to name if that works for you. I just wanted to try to give you a little bit more of a refresher. So with Mg3N2, that formula is going to split after the metal or ammonium. So we would split it between Mg and N. So we're going to name Mg and we're going to name N. Mg would only have a charge of +2, and nitrogen, being in group 15, can only have a charge of -3. Because magnesium is not a transition metal and it's not one of the exceptions, it just gets named by its full name, magnesium. And N just becomes nitride. We take the root and add on IDE. In the second example, we don't have a metal present to begin with. We have ammonium. We have that polyatomic cation. So we're going to split our formula between the cation and phosphorus. Ammonium is NH4+1. Again, you just name your polyatomics how they are. Phosphorus is in the same group as nitrogen, so it has a -3 charge. NH4's name is ammonium. And then P, we go from phosphorus, we would take the root of it and add on "-ide", phosphide. If for some reason you called it phosphoride, I would not penalize you. I am not going to make a big stink over you knowing all the individual roots. I think you're going to get those down over time. In the final 2 examples, we're going to see one of the metals that can form multiple ions, SN. It's not in the transition metal section, but I said that lead and tin are 2 of the metals that have that potential. And so you're going to need Roman numerals. And we have to decide which Roman numeral makes the most sense for these 2 compounds. It should not be the same since you have 2 different formulas written. We're going to split the compounds after 10. And so we need to figure out what 10's charge is so that we know what Roman numeral to use. We're going to come back to that in a second because the anion is going to help us determine that. Carbonate, in parentheses, is a polyatomic. It has a charge of -2. And we have 2 carbonates present in this formula. Well, if we have 2 carbonates present, each one being -2, overall, the 2 carbonates would contribute -4 to this formula. If there's only one 10 present and its charge has to balance out that sum of -4, 10 would have to be +4. With that in mind, when we name it, 10 would get the Roman numeral for 4 after it, IV, and CO3 would just be named by its polyatomic carbonate. In the final example, again, we're going to split between SN and CO3. Same as what we had before, we need to determine what SN's charge is. Since SN needs Roman numerals, it can form multiple ions. CO3 is still going to be -2. That 3 that came after the O is part of carbonate, so we only have one carbonate present in this formula. If carbonate's -2, 10 needs to balance it out, and therefore 10 would have to be +2. So the only difference between those 2 formulas is the amount of carbonate present, and that amount of carbonate is present is due solely to the charge of that positive cation. So the last section we're going to talk about with nomenclature review is molecular compounds. You often sometimes hear them called covalent compounds. These are formed between nonmetals and potentially metalloids. They result in the sharing of electrons. Sometimes the electrons are shared equally. So they would be considered to have a non-polar covalent bond, and other times they are shared in such a fashion where the electrons are drawn towards one of the elements that's present as opposed to the other. Those would be polar covalent bonds. They have a much lower melting and boiling points than your ionic compounds. When they're in their solid state, they tend to be soft. We have lots of molecular compounds that are liquids and gases. The ones that we're going to focus on naming right now are the ones that are made from binary compounds, just 2 elements. Those roots that we talked about with ionic are going to play a role, but rather than using charges, because we're dealing with atoms, we no longer have ions, we're going to use prefixes to represent amounts. You should have seen these prefixes in your previous chemistry class. Take a look at them. If you have any questions, please feel free to let me know. So when we're writing names for our molecular formulas, or writing formulas for our molecular names, we want to make sure that we write the symbols for the elements that are present, and then we include subscripts to represent the amount of atoms of each element present. So in our first example, we have Tri-Boron Hexahydride. So we see boron there, so we know that we need to have a B for our first element, and that we have hydride. Hydride is coming from hydrogen, so we need an H. The 3 that I put after boron is because it's a tri, telling me that there are 3 borons present in this compound, and the hexa represents the 6 hydrogens. In my second example, dihydrogen monoxide, I've got hydrogen, H, and I've got ox for oxygen, O, and I have a di for the hydrogen, which means I need 2 hydrogens for every 1 O. Mon telling me only 1 O is present. I want you to notice with these compounds, I'm going to do one more and then I'll talk about the rules for naming. I'm not sure why these aren't in here. Sorry. Arsenic, As. There's only 1 arsenic present, so there's no prefix, so I don't have to include a number after it. Pentabromides coming from bromine, Br, and the penta tells me there are 5 bromines present in this molecule. Notice that all of the elements that were present in the first half of the compound were listed by their full name, and that they had prefixes as long as there was more than 1 atom of that element present. And the second half of the compound, you have the prefix always, whether there's 1 atom or more than 1 atom. You have the root of that element's name, and then you add on "-ide". So those are the rules that you're always going to want to follow when you're naming your molecular compounds. When I look at the first one, I know that P is phosphorus, is the first element, so I list it by its full name. No prefix is needed. There's only 1 phosphorus present. The second one, there will always be 3 components. The prefix, in this case tri, the root, chlor, and then adding on "-ide", trichloride. In my second example, S is sulfur. Sulfur is actually going to need a prefix because there's 3 of them present, trisulfur. And as I said before, with the second element, you always need the 3 components. So even though there's only 1 O there, you still need to include the mon, and you need to end it with "-ide". Some of you may want to write that as monooxide. When the vowels that connect the root to the "-ide sound good, we keep it, and if they don't, we tend to drop 1. So rather than saying monooxide, we call it monoxide. That is not something, again, you would be penalized for. B2F4, B is boron. Boron has more than 1 atom, so we need a prefix, diboron. And again, with F for fluorine, we need all 3 components. We need tetra for 4, fluor for the root for fluorine, and then add on "-ide", tetrafluoride. All right, and these are common compounds that you should have seen in your first year class. Ammonia, water, hydrogen peroxide, methane, ethane, ethanol, and benzene. I do want to make sure that you know these compounds. Again, they will be up on Quizlet. You may want to make flashcards for them, but you are expected to know the names and formulas of these common compounds.